Hello, Adam.
Hello, sir.
Good afternoon or good day to you. How are you today?
I'm good, sir. How are you?
Doing good as well. Thanks for asking. Okay. So last time, I'm just going to um. Okay. So last time we were doing something like what was that? Oh yeah, lenses, right? Okay.
Yeah.
So is that clear to you now? How to draw the diagrams for lenses?
Yep.
All right.
I'm confident.
Okay then. So in that case, all right. So in that case, I think the next. Do you have anything else you'd like to go through before we go back to revising the papers?
I don't really have anything to go through.
All right. So
I'm studied and I'm good.
all right. So let's just continue revising the papers then. Okay.
Okay, so you are
Uh,
sharing your screen though.
yes. Hold on. Okay. I'm sharing my screen and I'm also sharing the Jamboard. Oops. Sorry. I'll change the view. Excuse me. Which one? Okay. Oops. Let's get rid of that. Okay, so let's start with this paper first. This is where we started last time with the lens question, right? Okay. This is done. This is done.
Yeah.
All right, let's go to question 2. So we have this figure 4 here shows the apparatus used to investigate the waves on a stretched string. And then the frequency is adjusted so that we have this. At this frequency, the string vibrates between the two positions like so. So, okay. First question here would be, so the wavelength is measured as 80 centimeters. So, of course, this should be an easy one to answer. What piece of apparatus would have been suitable to measure this?
A meter rule.
Okay, a meter rule, correct? All right. Okay, that's a meter rule. Okay, and then this next one, write down the formula or the equation that links frequency, wavelength, and wave speed.
Wave speed equals to frequency times wavelength.
Correct. Okay, so this is speed equals frequency times wavelength. Right. Okay, let me just note these down. Meter rule. And then speed, wave speed, is frequency times wavelength. Okay. All right, next. Okay, so the string vibrates at 55 hertz, so you must calculate the speed of the wave as shown in figure 4. Use the data given in it. Okay. So I'll just put this here. I'll just put this information here as well. So calculate the wave speed.
The answer is 44 meters per second.
44. How'd you get that? That is correct though, yeah?
Yeah. So since it's measured in meters,
Mm-hmm.
I would convert the 80 centimeters into 0.8 meters.
Okay.
Since it's V, v is 55
Okay.
hertz,
Correct.
vibrates at 55 hertz. It'll be
Okay.
55 times 0.8, which is 44.
All right. So this is correct. Where's the third mark? In case you're wondering, the third mark is the conversion here. So that's first mark. This is the second one, and this is the third one. Okay. All right.
Yep.
Okay. Okay. So so in this case now the frequency of the signal generators increased, but the wave speed stays the same. Describe how the apparatus could be adjusted to show one complete wave without reducing the frequency. Okay, hold on. Okay. So this again, so the wavelength changes, the frequency is increased, the wave speed stays the same. Describe how the apparatus could be adjusted to show one complete wave without reducing the frequency. I'll just copy the diagram.
You could change the mass and weight on the string,
Mm-hmm.
and you could add more weight and mass to the string.
Okay.
You can add more and change the
Okay, here.
weight.
Okay. Actually, that wouldn't be the answer here. The mass here, I'll just tell you what the purpose of the mass here is. This is to keep the string taut. Okay. It has an effect on the frequency of vibration essentially, but in our current setup, it's really just to keep the string taut. Okay. And nothing much else. Okay, so the answer here doesn't rely on the masses. Okay, I'll give you a hint just to make it a bit easier. Remember that the wavelength will change, right? So in this case it's increased. So can you tell me the type of change that you'll see here? Because of the fact that this happened, what is this change? Is it a decrease or an increase?
Decrease.
This is a decrease. Okay, if that's a decrease, then if you draw this here on the diagram, then it should look a little bit something like that now for one full wavelength. So what can you do to get your one full wavelength?
You can move the bridge more to the right.
Okay, move the bridge to the right. Okay, so that would be your 2 marks, identifying what kind of change is happening. So you have to say this, yeah. What's this? The wavelength decreases. And thus, okay, the wavelength decreases. To okay, that these 2 statements are your 2 marks. Okay.
Okay.
Okay, great. Okay, a student wants to investigate how the speed of a wave on a stretched string depends on the tension on the string. The student uses the same apparatus. Okay, So describe a method that the student could use for this investigation. So this is what we just talked about. Okay.
Okay.
All right. I did mention earlier that the masses here are to keep the string taut. But if you think about it, the more masses there are, the tighter the string is, right?
Yeah.
Okay. So keep that in mind as you answer this question here. Put this here.
I'm just gonna write down my answer then.
All right, sure.
It's just that I'm taking notes on all the questions. That's it.
Okay, sure. Again, Adam, I am recording this, so I'll share with you the link later on YouTube. Okay.
Okay. It's just that I also prefer to write so I can memorize as I do it. That's all.
Okay, sure. No problem.
Okay, I got it.
All right. So, okay, what are the first?
You need, yeah.
Go ahead.
So you need to add or take away masses from the string.
Okay.
Just the frequency using the single generator,
Okay.
and or move the wooden bridge.
Okay. Move the bridge. Okay.
Observe a stationary pattern. Measure the wavelength.
Okay. Observe station. Okay. All right. And then the last step is.
Calculate wave speed or frequency
Okay.
and wavelength.
Okay. And then finally calculate speed from wavelength and frequency. Okay. Correct. Okay. Okay, this is not or, this is and. Okay. All right. I think you can get 4 marks on this one, so no problem. All right, get. It's good. So let's continue. Okay, so that's the last question there. Let's take a look here in 3. So you see, do you have a driver on a vehicle seeing a hazard on the road? Then the driver uses the brakes to stop the vehicle. Explain the factors that affect the distance needed to stop a vehicle in an emergency. Okay, it's 6 marks, interestingly. So, how do you get 6 marks for answering this question?
Okay, I'm just gonna write down my answer.
Sure. Tell me when you're done, and I'll help you type it in here. Okay.
Okay, I got an answer.
All right. So what's your answer here?
I got. So reaction time would be the main issue.
Hmm?
Explain it. So since the longer the reaction time, it increases the thinking distance.
Mm-hmm. Okay.
And these factors can be affected by taking drugs, tiredness, age, distractions,
Okay.
drinking alcohol.
Okay.
Yeah.
So,
And the speed of the car itself.
okay. What about the speed of the car? Can you explain that further? Because I think at that the one you have
faster
is
the car is going.
okay. Go ahead.
Yep.
Mm-hmm.
The faster the vehicle is traveling,
Mm-hmm.
the slower the reaction time. The slower the reaction time in terms of,
Okay.
sorry, shorter the thinking distance.
Okay. All right. I think out of 6, I'll give you 4 for that. Okay. You got the reaction time right, so I think I can give you 3 for that part. Okay. For the speed, it's not that the reaction time becomes smaller. Your reaction time still gonna be the same. So the thinking distance still, but because of the bigger speed, that means the thinking distance is now longer as well. Okay. So the reaction time becomes longer because of, as you said, increasing thinking distance. But the speed itself plus the longer reaction time means you also increase further the thinking time. Okay. About the speed, what could okay, so about another possibility here is saying something about the condition of the car. So it could be the tires, the surface, the road, the brakes, those things. Okay. Also, you mentioned a long time ago, you mentioned mass and weight of the vehicle can also affect this. Right? Okay.
Yeah.
All right. So, okay, let's go to the next question. Okay. Write down the equation which links distance, force, and work done. The equation for...
Work done equals to force times distance.
Okay, correct. All right, let's go to the third one. The work done by the braking distance is given here as 900,000 joules, and the braking force is 600,000 joules. So, calculate the braking distance of the vehicle. You can do this one of two ways. You can use work done or you can use SUVAT. Which one is a lot easier in this case?
Sorry, asking me a question?
Yep. Actually, I'm not really asking a question. It's more like just saying something. Okay, go ahead and just answer this.
The answer is 15 meters.
15 meters is correct. Okay. Okay, I'll just finish that later. Okay, so that's one. That's another. Correct. Can you tell me how you got 15 meters? 15. Yeah, 15 meters.
900,000
Divided by
60,000.
60,000. Okay. This is joules. This is newtons, and that's gonna give you 15 meters. Okay. Let me just double check. I think you get your first and second marks for this working. Yeah, you get your full 3 marks just for this
I
working.
mean, first you would write 900,000 equals to 60,000 times distance.
Yeah.
Okay.
Okay, so that's that and there. Okay, so correct. You get 3 marks full. All right, let's move on. Okay, the greater the braking force, the greater the deceleration of the vehicle. Explain the possible dangers caused by a vehicle having a large deceleration while it's braking. Possible dangers of braking too fast.
Brakes overheating or brakes locking.
Say that again.
The brakes overheating or the brakes locking up.
Okay, correct. Okay. Now what effect does that do? What effect does that have rather?
That causes a loss of control or a skid.
Okay. Okay, so yeah, that's correct. So the greater the deceleration, the greater. Okay. How can we say this? I think that's good enough. All right, to get full marks on that. Okay, so let's take a look here on the solenoid. Okay, figure 5 shows a solenoid. First of all, draw the magnetic field on this solenoid. So you really have to draw this. Okay. So draw the magnetic field around here. Okay. You've learned this before, right? Magnetic fields?
Yep.
All right.
So there will be field lines going through, and like through the left side, coming out of the outside, like the right. Sorry, going into the left and out of the right of the solenoid.
Okay. Okay, good.
And they would, yeah.
Okay, just so you're clear, yeah,
And
I
like
would.
arrows pointing in the direction.
Okay, I would normally draw it like this because this is a solenoid with a hollow tube. That means we can put something inside. So we have to draw the magnetic field. Oops. You have to draw the magnetic field on the outside as well, if possible. As you said, on the inside, it's going to point like that. So it's going to point like this, right? So I'm going to draw another one here. Something like this. Okay, then I could draw a third one. Similar to this. Okay. Alright, again, this is how I would draw this. Okay, and then, oh, sorry, other way. And then the last one, I'll just draw something like that. This is a possible answer, I think. Okay. Another possible answer is you're just gonna draw this section. You don't have to draw the... You're just gonna draw the inside and a little bit of the ends. You don't have to draw these. That's another possible answer. However, I would rather draw this version. This is a better version of the answer because it's all over the place, right? Okay. Alright, next question. So you have two iron rods placed inside the solenoid. Explain why those rods move away when the switch is closed. Interesting question. Why do they move away inside the solenoid? Two marks. What are the key words you need here for your 2 marks?
So the rods become more induced magnets.
Okay, both of them become induced magnets, and then why if they're both magnets, go ahead.
At each end.
Okay, become induced magnets with like poles on each end.
Yep.
Okay, 2 marks. Okay, so what would happen? Basically, what would happen? This the solenoid becomes our north pole here and a south pole here, for example. Then both of these rods will become north and north here, south and south here. So of course, like poles repel each other. Okay, that's actually good enough for 2 marks. Most people will probably answer something like like poles repel, so the rods repel each other. Okay. All right. Next. Okay, so now, okay, this is another investigation type question. So we have the strength of an electromagnet being investigated. So, okay, we have the apparatus shown here. He's gonna measure the strength of the electromagnet as the maximum weight that the electromagnet could hold. Good. So here are the results. Explain why the method used by the student is not valid here.
We answered a question like this before.
Yeah, we have, right? but not this exact question, I think.
Yeah. Yeah, I don't think so.
Not this exact question. I recall it being something else. But the idea is the same. Why is it not
The answer is
valid?
Yeah. Because they changed two independent variables at the same time.
Correct. Two independent variables are being changed, so
Therefore, variables.
say that again. Sorry, your audio broke up there.
Therefore, you cannot possibly know
Okay.
the effect on one of the independent
Okay.
variables
Correct.
or the other.
Correct. So, two IVs are being investigated. Hence, it is not possible to know which one is causing the change, right? This is again good for 2 marks. Okay, next. Okay, so you have a second student repeat the investigation using the same experiment, and there's a graph given here. This is gonna take some space, so I'll put a new board up. Let's put a new board up here. Okay, so how does increasing the current, so the first question here is, how does increasing the current in the wire affect the strength of the electromagnet when the electromagnet has 30 turns?
Increasing the current increases the strength until the strength reaches a maximum value.
Okay. Okay, correct. Okay, maximum value. And what's the value of this maximum that we have here?
It's about like, can't see it very clearly.
Okay.
It's, let's say 7. No, not 7. It should be around like 11.4.
Correct. So around 11.4. Yeah. Good. So, how does increasing the number of turns in the wire from 10 to 20 affect the strength of the electromagnet? Compare that to increasing the number of turns of wire from 20 to 30. So first from 10 to 20, and then from 20 to 30.
Increasing the number of turns from 10 to 20 will automatically increase the strength more than increasing 20 to 30.
Okay, good. So, okay, right. So how do you say that? Remember, the best possible answers always state like an observation here. Okay. So what observation can you make?
A general trend is required.
Okay, what do you mean by that?
As in there would be a constant trend strength when increasing the turns.
Okay. How does one? So the idea here is that you really have to look at this jump. Okay. Generally speaking, the jump from 20 to 30, no matter where you look at, is bigger than the jump between 20 and 30. So in all cases, like here and here. Okay, for the same number of amps. I would say it that way to be safe. Again, at this point, you could keep saying something like this, but you never know what the marking scheme has at the end, right? So it's better to just hit all your bases and say a more specific answer according to the graph. Okay, so this is what I would write, just so we're clear. Okay, throughout all current values, the increase of, or the jump from the jump in the weight increases more increases more for between 10 and 20 turns as compared to 20 and 30 turns. Okay. Yeah, this is how I would say it, just to be safe. Okay. All right, I'll just copy this other one here. I'll just one increases 11.4 newtons can supported. Okay, so again, generally I would say it this way, just to be safe. Okay. Okay, good. So the next one, okay, so we're done with the electromagnetic questions. Okay, let's go on to this one. The galaxies. Oh, we haven't done this yet, right? So we'll skip this. Big Bang, Andromeda. Okay, let's go to this question number 6. An adult of mass 80 kilograms has more inertia than a child of mass 40 kilograms. What is inertia? What is inertia? Next question. Okay, so Adam, what is inertia?
Inertia is the tendency of an object to continue in its state of rest or motion.
Uh-huh. Okay, now this is a definition, so you really have to memorize this. Okay. So then I would say it like this: tendency of a body or an object to maintain its current state of motion. Again, because it's a definition, this is how I would say it. Okay. All right. So the second one. Explain why the egg is less likely to break when dropped onto soft foam than onto a concrete floor. There are many ways to answer this. But all of them kind of lead to the same final answer.
Soft foam increases the time taken to stop, or it will increase the time taken to decrease momentum,
Okay.
which would decrease the rate of change in momentum,
Okay.
reducing the force of the egg.
Okay. All right. So how does so again, I'll just state here how I would actually write it down. Okay. So always write this down in terms of force equals either MA or force equals the change in the momentum per unit time. Okay. So okay, the way you stated is going to answer that in terms of this for change in momentum over time. So in this case, actually for both cases, yeah, time to slow down, time to stop increases when foam is present, right? Okay, so that's the common answer in both cases. The time to stop will increase when the foam is present. And how will these diverge? The first one, the one you said, is the change in the momentum is the same. So from the equation F equals change in P divided by time taken. The overall force will decrease. Okay. Then the overall force decreases as well. Okay, so this will gain you your, how many marks was this again? 3 marks. The first mark will always be about the time. The second mark is here. Okay. All right. All right. How would you answer this in terms of F equals MA? It's going to be the same idea. Okay. It's going to be the same idea. So instead of looking at the change in the momentum, you're looking at the acceleration. The change in the speed. Okay. The change in the speed is the same. So we do here M equals MA. Not yet. So this decreases the acceleration of the egg. Okay. With the equation F equals change in mass times acceleration, the overall force decreases. Okay. So again, these would be two possible answers. I think in this case, the safer answer is always the momentum version. Okay. This is the safer answer here.
Okay.
Okay. All right.
I'm just writing that down.
Okay. Okay, next question here is, you now have a child on a playground swing which has a rubber safety surface. Okay, a child of mass 32 kilograms jumped from the swing. when the child reaches the ground, she took 180 milliseconds to slow down and stop. During this time, an average force of 800 newtons was exerted on the ground. Calculate the velocity of the child when she first touched the ground. This is a 4-mark question. So I'll put this in here on the Jamboard. Okay, so if you need help, you can always refer to the previous slide.
Okay.
Okay. Which equation would be the fastest one to use here? Because you're looking for the velocity, right? When she first touched the ground.
I mean, there's two methods. There'll be one, I just need to rearrange the equation.
Mm-hmm. Okay, there are actually three. If you really think about it, there are three methods.